Okay, so we've set the anhydrine prints aside. We're going to do the Indanedione zinc chloride prints now. So if you recall, we've already put prints on these sheets here. As I said, they're independent of one another. This is another amino acid reagent that we are going to use. The difference between this versus the anhydrine is when processing Indanedione zinc chloride, it's a double dip system. So you saturate it first in the solution, set it aside to air dry, and then reapply it again the second dip and allow it to dry the second time. And after it is air dried, research is suggesting that it should go into a heat press and be pressed at 165 degrees, 160 degrees Celsius for 15 seconds. Again, we don't have a heat press here, so we are going to improvise. We have one of the hot plates here from the chemistry section, and it's been preheated. What we're going to do in lieu of that is, after I dip this twice and allow it to air dry, we're going to put it inside a file folder here because we don't want to scorch the paper, and we're not sure what that temperature of that hot plate is. So we're going to put the paper inside the file folder, place it on the hot plate, and then to assist with the dispersal of the radiating heat, we're going to put a galvanized plate on top to try and evenly disperse the heat on the other side as well. And we'll leave it in there for several seconds and see what kind of results we get. Now, the other advantage with the Indanedione zinc chloride is that it will also show potentially pale pink colored fingerprint, but it can also react further visualization with an alternate light source and the KV550 orange barrier filter. So we'll get to that after the fact. One other thing of note is that the sensitivity of these chemistries, the anhydrine, the first in that sequential process, that DFO solution is 25 times more sensitive than anhydrine to the amino acids, and this is 10 times more sensitive than the DFO. So this is a very sensitive chemistry reacting with a wide range of the amino acids. So a very fairly new formulation, at least in the forensic world. It's only been around for about roughly 35 years, but for you folks that are all either 20 or 20-ish, that seems like an eternity, but in the forensic world, 35 years is not very long. It's fairly new, but a very successful chemistry, and one that is being used by, it's gaining significance and general usage throughout the forensic community and many agencies that process fingerprints on porous surfaces. Okay. Okay, so this chemistry, we got the working solution here of the Indanedione zinc chloride, and so I will pour some into the tray here. Just set that aside. We've got our paper sample that's already got the fingerprints in it. And again, as we discussed, we do one dip, and we are going to air dry that. So we'll set that aside and allow it to dry. And again, it will evaporate fairly rapidly, so we can do the second dip in just a moment. Okay, so after the first the dipping, it is now completely air dried, so we'll put it back in the tray and dip it a second time here. Shake off the excess, and we'll set that aside to air dry again. Now, one thing of note, the solvent that we use in this particular chemistries is HFE 7100, which is a 3M product. It's an engineered formula, and it works ideal for this as a substitute solvent for some other ones like petroleum ether and that kind of thing. Okay, so I'm just going to put the tray aside now here into the fuming hood. And our sample is almost dry here. So I'll just bring the other pieces in that we're going to use. So we've got this file folder here. It doesn't necessarily have to use this system. We simply use it to help prevent the scorching of the paper from the high temperature of the hot plate. So put that in there. I'm going to put on this UV glove here, which is a temperature. It's going to prevent my hand from getting burned when I hold this down on top of the hot plate. And so I'll move the hot plate over here so we can see what's going on. And so we'll put this down now, and we'll put the galvanized plate on top, and we'll simulate our 160 degrees Celsius for 15 seconds. When I start to smell flesh burning, I know we're just about at the right temperature and timeline here. Because we don't know what the actual surface temperature of that hot plate is, or what the temperature inside that file folder is, we'll just leave it here for a longer period of time, and we'll just take an estimate of when it might be fully developed. Feel the heat transfer through the glove. Okay, so let's have a look and see what we've got now. So we set that aside, and here we can see spectacular development with this pinkish color. In casework now, when I was still doing casework, this would be my go-to chemistry for developing prints on porous surfaces because of its sensitivity and how successful that appears. Now, as you can see, there's several prints appearing this pinkish color, but it will also react, as we said, further visualization with an alternate light source and orange barrier filter.
Now we are going to look at the processed Indanedione fingerprint on porous paper, and we're going to look at that once it is visualized using our alternative light sources. So we have 3 to choose from that are in a very similar range. We have 450 nanometers, 505 nanometers, and 530 nanometers. All of them will produce a color because the excitation range for this is quite broad, but you'll see at which wavelength has the highest intensity. So obviously we have our orange filter back on, and I'm wearing orange goggles as well to protect my eyesight. I'm going to start with a 450, which is a blue light. There we go. So you are seeing it pop up there. It's more in. Then we are trying with a 505. You see a bit of the teal in the background. But that palm print is very visible and very bright. And lastly, with the green 530 nanometers, this is how it looks like.